Hey guys, these are your notes for section 9.1 day 2. Still working on limits. Still working on sequences, which is just a list of numbers, okay? And by the way, we're not getting into series yet, but the difference between a sequence and a series, a sequence is a list of numbers, like with commas. A series is when we take that entire sequence and add all the terms together. We're not there yet. We're just doing sequences for right now. So we're just looking at lists of numbers. That's it. And today we're going to determine, hey, if we look at that list of numbers, where is each of those numbers? Where are they headed? If we keep that list going, do the numbers just get bigger and bigger and bigger and head toward infinity? Or does each term approach an actual value like 0? Or does each term get closer and closer and closer to the fraction 7/6 or whatever, So we're going to see if the sequence converges or if it diverges. So, this is kind of the definition. It's kind of wordy. It's very mathy. And here's the thing. If the terms in a sequence just keep getting bigger and keep getting bigger and we're going to say that if the terms are headed toward infinity, the sequence diverges. Just kind of gets out of hand. However, if we can prove that each term, if I write more and more terms, each term gets closer and closer and closer to a single value, then we can say that the sequence converges. And that's what this whole big paragraph says. Let me make this a little easier for you. We're going to do a limit on our sequence. We may look at our terms individually, or we may look at an explicit rule for our sequence. But we're gonna do a limit on our sequence. We're gonna figure out where are the terms headed. If you keep going and you keep going and you keep going and you keep going, where are they headed? And it's gonna look like this. We're gonna do the limit as n approaches infinity of a sub n. Where are the terms headed? If I can get a definite value called whatever, L, I can say that the sequence converges. If I get an answer like positive or negative infinity, then I'm going to say that the sequence diverges. Since we're doing limits, this is just a good reminder of what's legal when you're doing limits. Pretty much anything you want to do with a limit is legal. Pretty much. So this is saying, suppose that the limit of this sequence has an answer of L, and the limit of this sequence has an answer of M. So if you want to add those two sequences together, you can do the answer to this limit plus the answer to this limit. Okay? Multiply them, divide them, as long as the answer to that limit, this one, doesn't equal 0, of course, obviously. You can subtract them, and if you've got a constant in the way, feel free to pull your constant out to the front. Okay, here we go. So this sequence is defined explicitly. If I wanted to jump to the 100th term, I could certainly sub in 100 and I could find the 100th term. Now, remember how I said this is going to get pretty hard in third quarter. So a lot of times, just for fun, or maybe just for some more clear understanding, I like to write out several terms in a sequence, even though it doesn't tell me to, even though I wouldn't really have to in order to solve this problem. I just want to know what's going on with this sequence. So just for fun, I'm going to go a sub 1 is equal to 2 times 1 minus 1 over 1. Okay. I wrote out 6 of them. 1, 1 1/2, 1 2/3, 1 3/4, 1 4/5, 1 5/6. So yeah, the terms are getting bigger, but I don't think they're headed toward infinity. So in order to solve the problem, let's do a limit on it. Let's do a limit as n approaches infinity of a sub n. Well, how is a sub n defined? It's defined by that explicit equation. And if you remember about limits, when the degree of your numerator is equal to the degree of your denominator and you're headed toward infinity, the answer to your limit is your leading coefficient over your leading coefficient. What this is saying is each term will get closer and closer and closer to 2. Will it ever reach 2? No, but 2 is the value that it's headed toward. So since I got a definite answer, a value for when I did a limit on it, I can say that this sequence converges. Moving right along. Just for fun, I'm going to write out a few terms. And you can see that they alternate in sign. And where are they headed? Well, I believe that if we ignore the fact that every other one is negative, I believe my fractions are getting closer and closer into 1. Each of these fractions is getting closer and closer to 1. However, they're alternating in sign. So technically, my odd number terms are getting closer and closer to -1, and my even number terms are getting closer and closer to +1. I think that the farther out we go, the more this is going to look like a sine or cosine wave. Just oscillating from 1 to -1, I mean, not quite 1 and not quite -1, but you know, that's what the graph is going to look like. So I know that this diverges. Also, if we did a limit on it, we certainly can. The limit doesn't exist. If this part weren't there, if the whole oscillating signs weren't there, I could say as n approaches infinity, this sequence is headed to 1. But since this is here, that means it's oscillating back and forth between positives and negatives. Just because, I'm pretty sure this is a true statement, just because a sequence oscillates in sign, S-I-G-N, does not mean that the limit doesn't exist. Because each fraction could be getting smaller and smaller and smaller. I could be approaching 0. But I'm not on this one. So it diverges. Okay, next one. And now for some reason we switched letters, so the representation of our sequence isn't a sub n, now it's b sub n. Don't know why, just go with it. So first term is 4, second term is 6, it's defined recursively. Third term is 8. You can see what's going to happen here. limit as n approaches infinity of b sub n minus 1 plus 2. So that diverges. Okay, next one. Last one. Squeeze theorem. It kind of defines what squeeze theorem is. How about you let me explain it to you? We are going to show that, show that the sequence converges. It's kind of like we're doing a proof, okay? Show that it converges, which means we got to do a limit on it. I got to do a limit as n approaches infinity of cosine of n over n. Whew. So here's the thing. You all know what cosine of x graph looks like. You don't know what cosine x over x graph looks like. If you knew what the graph looked like, you could say, oh, okay, well, as n approaches infinity, I'm just going to take my eyes way out to the right on the graph and see where the function is headed. You know what the graph looks like. You can't do that. So I'm going to show you this thing called squeeze theorem. Squeeze theorem works really well when we're doing limits on sine or cosine. I'll tell you why in a minute. So I first want to give you a picture of what squeeze theorem kind of looks like. Suppose we are looking at the pink function. The pink function is kind of what it's all about. So we're looking at the pink function, let's say just between a and b, okay? We're not looking at it everywhere, just between a and b. Take a look at the pink function. We don't know what its y values are. However, here's what we do know. On that interval, according to what the graph looks like, I know that my pink function is always, let me write it correctly first. My pink function is always bigger. My pink function is always, the y values are bigger than the green one. And the pink function is always smaller than the blue one. These y values are always bigger than or equal to these. These are bigger than these or equal, and they're always smaller than or equal to the blue. Okay? That is a true inequality. It's a true mathematical statement. Without a shadow of a doubt, if you look at that picture, you know this to be true. Okay? So, let's go back up to here. We're going to use kind of that concept to figure out this limit. So again, remember, you don't know what this looks like, but you do know what cosine looks like. So I want you to just grab cosine of n. Just grab that. I'm going to write it on my paper. Cosine of n. Now, if this is your pink function, can you tell me, hey, I know that cosine, do you know a fact about cosine? Cosine is always between two specific functions. Or how about this? Two specific constant functions. Or between two specific values. You know this. On a graph, you know what your cosine graph looks like. You know that cosine never gets above 1 without some type of structure transformation, and it never dips below -1. Right? So we took a piece of our function, of our explicitly defined sequence. We took a piece of it and we turned it into a true mathematical statement. True mathematical statement. You have to start with a statement that you know beyond a shadow of a doubt, without using your graphing calculator, is true. Now, does what I have written here look like my function? Nope. It's missing the divided by n part. Can you legally manipulate this mathematical statement so that your middle piece looks like cosine n over n? Well, sure you can. Divide the middle by n. But if you divide the middle by n, keep it legal, divide the left side by n, and divide the right side by n. Divide by n, divide by n, divide by n. Here's what I get. This is something I bet you didn't know. This function, which you don't know what it looks like, is always between this function and this function. I would not have known that had I not come up with that legally. I knew this one. I didn't know this one. Okay, so that still doesn't help us like with our limit. We just have our function written that this function is always between these two. Better yet, I want to know what happens as n approaches infinity. So now you need to throw on this part in all three sections. I need this to say the limit of cosine n over n. So you need to throw on a limit here, keep it legal, throw on a limit here, throw on a limit here. I'm going to go, and I'm going to run out of room. Limit as n approaches infinity. Limit. I know it's a lot of writing. Get over it. Limit. Okay. Alrighty. Almost there. Do you know the answer to the middle? No. If we knew the answer to the middle, we wouldn't have had to do all this work in the first place, right? I don't know the answer to the middle, but I can figure out the answer to the left. As n approaches infinity, this becomes negative 1 over huge. My answer to this limit is 0. This one we don't know. And the answer to the right side, we can figure this out. As n approaches infinity, this becomes 1 over huge. The answer to this limit is 0. So, as n approaches infinity, this is headed towards 0. So I can say the limit, it's kind of like I'm kind of like summarizing, writing my answer. As n approaches infinity of cosine of n over n equals 0, so the sequence converges. Oh, hang on. That's what our answer looks like. We have to be able to say that we use the squeeze theorem to determine that the answer to this is 0. And since the answer to this is 0, I can say, okay, yeah, the sequence does converge. Okay, so when you use the squeeze theorem, you're supposed to mention the squeeze theorem. And there's not really an abbreviation for it, like mean value theorem, you can call it MVT. Just gotta write out squeeze theorem, sorry. Alrighty,